Okay, so you have here, it takes more force to start an object moving along a surface than it takes it moving, keep it moving once it has started. Basically, there are two types of friction. So if I can just write at the side, we have what you call the static friction, and we also have what we call the kinetic friction, kinetic or sliding friction. Uh, their formula is basically the same. However, for the maximum static friction, it's equivalent to mu s times the normal force. And kinetic friction is just given by Fk or Ff sub k mu k times Fn. So the mu's here just indicates the coefficient of friction, static friction, and the coefficient of kinetic friction. Well, based on experiment, mu s is always greater than mu k. The reason for that is, again, from the previous statement, that you need more force to start an object moving along a surface than to keep it moving once it has started. So I guess if you have also observed this one, if you're trying to push a table, at first it's very hard for you to move it, but once it's moving, you can feel that there's a decrease in the amount of force that is going the opposite direction. So the reason for that again is your mu s is usually bigger than your mu k. So given everything as the same, like the normal force, so you're talking about objects of the same mass, and they're lying horizontally, as well as you're talking about the same type of surfaces, the mu s there is bigger compared to mu k. So if you can observe, I just want to emphasize the maximum static friction here. The maximum static friction is given by this formula mu s times Fn. But that is only true for the maximum static friction. Okay? Because let's say, for example, if you have an object, okay, lying horizontally on a surface, we know that you have several forces here, Fg, and then Fn, and then let's say for example, in this case, the maximum static friction is equal to 50 newtons. So in this particular case, again, in this particular example, the maximum static friction is 50 newtons. So meaning that you can only move the object once you overcome that 50 newtons. However, in a certain question, let's say for example, you apply a force to the right that is just 30 newtons. So do you think the object will move in this case? Object, will it move? No, it won't. Because if you're gonna count the magnitude of your friction, and in this case, it's not moving, so the friction that is present here is the static friction. Okay? So the static friction in this particular case, since it doesn't move, so this is the same thing as what we had earlier, that the magnitude of this normal force, no movement vertically, so the magnitude or the length of this upward force and the downward force would be the same. So as well as these horizontal forces, that should also be equal. So if the object doesn't move, static friction is just equivalent to the normal force. And again, that is if it doesn't exceed your maximum static friction. So if I have another force being exerted there that is, let's say, 10 newtons, so the static friction is also 10 newtons. If I exert a force of 45 newtons to the right, so that means that if I'm gonna change my force to 45 newtons, my static friction also changes. So basically speaking, if you're gonna look at the value of the static friction, it's not fixed. Okay? It depends. The one that is fixed is just the maximum static friction. Okay? So this is the minimum force needed. So the Fs max is the minimum force needed. Force needed to move an object. So that would be the significance of the maximum static friction. That means that if you're going to exert 15 newtons, that is now in the brink of moving. So now, once it moves, what is present there is already the kinetic friction. And the kinetic friction is given by a different formula. But again, it has a basic form of the formula. It's just the product of mu and the normal force. It's just that for surfaces, again, mu s, for a particular surface or a set of surfaces, mu s is greater than mu k. So the mu s there, if you're going to multiply the mu s and the normal force, it gives you the maximum static friction. It's just not static friction, okay? Because if you can see in our example, again, the value of your static friction ranges from 0 to the maximum static friction. So it's within that range. Again, some sort, if you only apply a force, there would be a static friction. But if that applied force is not greater or equal to the maximum static friction, the object will not move. So if you can see, again, in a particular problem, you can also observe this one. If you're pushing a table, even for a slight force, well, the object will not move. The reason for that is there's static friction. And the maximum static friction is bigger compared to the force that you exerted. Okay? So once you increase the force, well, the static friction also increases until such time that you overcome the maximum static friction. So again, if you can see that the formula is just the same, the subscript just changes. But I just want to emphasize again, for the static friction, it doesn't have a fixed value. The one that has a fixed value is the maximum static friction. But if you're exerting a force that is less than the maximum static friction, that would also be to be expected, since you're pushing the object and it doesn't move. So according to the first Newton's law, the net force along that direction is also equal to 0. So the net force is 0. If the net force is 0, that means that, well, if you only are talking about two forces opposite in direction, so their magnitude must be the same. So let's take example number 4 here. A 500 Newton is used to push a 200 kilogram box along a surface that has given 378 frictional force. So what is the acceleration of the box? Okay. So in this particular case, you're already given the magnitude of the friction, which is 378 newtons. But then again, make it a practice to draw the free body diagram. So if this object is lying horizontally on the surface, so I have Fg. Again, in our case, Fg, the weight of the object can be determined by the product of your mass times the acceleration due to gravity. Normal force, this object is not moving in that vertical direction, so that means their magnitude would be the same in this case. And then I have an applied force. I'll just make that it's to the right. So that's 500 newtons. And then the frictional force. So frictional force is given. So this is already given. So that would be my FF, which is 378 newtons. So from that figure alone, I know that there's no vertical movement. Okay, it doesn't move up or down, but FA is greater than FF. So that means that there should be a net force acting on the object, and that is along the horizontal. So that is along the x-axis. So that means that the acceleration would be along that x-axis also. So for our solution, well, the net force is no longer equal to 0, but this time it's equivalent to MA. So net force is equivalent to MA, or since we're solving for A is equal to F net over the mass. But where does that net force? Well, net force is not equal to 0 along the X. So I'll be focusing the forces along X. So in my solution, I'm just gonna expand my net force. My net force is consist of FA. Again, FA, so I'm gonna use the right as my positive direction. So that's my positive direction. So that would be positive A plus the negative of the magnitude of F, okay? And then divided by M. So again, these are my forces along X. So again, I'm expanding that particular net force, because net force means I'm taking the sum of all the forces. But again, in this particular case, I know from the free body diagram itself, the movement will just be horizontally. So that's why I don't mind about the Fn and Fg in this particular case, because what I am trying to get is the acceleration, and the acceleration only happens along the x-axis. So all of these are x components of the forces. So that would be 500 minus 378 divided by 200. So this gives me, so the magnitude, this gives me the magnitude, but if you can see, this is positive value, positive 0.610 meters per second squared. Again, I'm gonna write this one, changing the positive symbol. It only means that this is moving to the right. Again, it is to the right because I set that one, that positive is to the right. So this one here, I set that going to the right is positive. So therefore, in the opposite, the negative sign will indicate that the object will be moving in the opposite direction. Okay. So now, in this particular case, we employ second Newton's law because the net forces is not equal to zero. So if it's not equal to zero, there must be an acceleration. And the net force is just equivalent to the product of the mass of the object times the acceleration of the object. Again, that is according to the Newton's uh, second law. So let's take example number 5. What force is required to give a 70-kilogram person an acceleration of 0.82 meters per second if the coefficient of friction is 0.422? Okay. So what force is required? So in that particular case, you're talking about the applied force. Coefficient of friction is 0.422. So to have a better picture of the problem, again, start with your free body diagram. So you have a person. I'm just going to represent that one by the dot. So what are the forces? Well, again, you have Fg, that is downward, and that's equivalent to Mg. And if you're going to solve for that, that is just 70 times 9.8. So that gives me 4,900 newtons, okay? And I have Fn. So in this particular case, there's no movement vertically. So that means the normal force is just equivalent to Fg. So that means that Fn should just be equivalent to your weight, the magnitude of the weight, which is 4,900. So that means that this is also 4,900 newtons. Again, that is using the fact, well, I already see in my free body diagram in the vertical components, there's no other forces except for Fn and Fg. And these two forces are in opposite direction. So if they're opposite in direction and their net force is equal to 0, it also follows that the magnitude of your Fn and Fg must be the same. Okay. So now I'm looking at the horizontal component. So let's just say the positive is to the right. So right direction is positive. So that means that my applied force must be to the right. Fa.
Mr.
And that's, yes.
Sorry, so when do we know if the net force is going to be 0?
If the object is at rest or moving with a constant velocity.
Oh, okay. Got it.
So the object is at rest, automatically the net force along the it's either S or Y components. So that means the sum is 0. Or
Okay.
if it's moving, it should be moving with a constant velocity.
Got it. Okay, thank you.
You're welcome. So we have our friction. There should be friction in this particular case because, well, you're given the coefficient of friction. So indirectly, it's not mentioned in the problem that you have friction, but by just placing that the coefficient of friction is not equal to 0, so there must be friction. And that friction, this again, you're moving horizontally, so it must be on the horizontal axis also, but opposite to the movement. So that would be my FF. Okay. But in this question, what we have is just the mu coefficient of friction. We're not given the value of F itself. However, again, if we're gonna emphasize the given quantities. This is 70 kilograms. Well, Fg is 4,900 newtons. That's why I also know that Fn is 4,900 newtons. And I given the value of mu, which is 0.422. So that would be, again, the coefficient of friction. So I'm trying to solve for Fa. So going through my solution, by the way, I'm also given the acceleration, which is, this is just the positive 0.82 meters per second squared. So for my solution, there's an acceleration of an object. So I know that if the object is accelerating, the net force is just equivalent to the product of its mass times its acceleration. Okay, so if I'm gonna check, do I have everything here? Well, mass is given, which is 70, and the acceleration is given. Okay, the acceleration is also given. So essentially, the net force can be solved. So I can solve for the net force. That means that the net force is just equivalent to the mass multiplied by its acceleration. The net force is equal to, that would be 57.4. So kindly check if, okay. But this is just the net force. What I'm solving is Fa. So how would I solve for that? Well, I can do that by expanding. I know that this F net here is consists of several forces. So what are the forces that consist your net force? Well, if you can see here, the particular net force is made up of your Fa and Ff. So you have Fa, which is plus, positive. I use the direction to the right as positive. And then plus, well, this should be negative Ff. Okay. So, Fa, therefore, so if I'm going to work with this equation here, I can see that Fa, so adding both sides by Ff, will give me the net force plus the Ff. Again, how did I get plus Ff on one side? Again, that is just basic in your solving equation. So I'm just gonna add Ff on both sides. So that's why I got Ff on the other side. So the applied force is just the sum of the net force plus the frictional force. Well, in my case, F net is already given, and that is given by 57.4. So I can substitute that 57.4 newtons. However, I don't know my Ff. So I need to solve first for my Ff in order for me to solve my Fa. So how would you solve Ff? Well, Ff is just the frictional force. And again, the formula for the frictional force is mu times Fn. So going back, mu is given, which is good. You have mu here. That's 0.422 multiplied by, well, you given the normal force. Well, normal force has the magnitude of 4,900. So therefore, that's given. So that's 4,900 newtons. Okay. So I can get the magnitude of FF by multiplying your mu and the normal force. And that should give me 289. Just try to confirm 289. 289. Okay, newtons. So now I can replace that value in my FF. So that is plus 289. 289 newtons is equivalent to FA. So now FA would just be equivalent to 346 newtons. 346 newtons. And it also makes sense that the applied force must be bigger. So the applied force must be bigger in magnitude compared to the frictional force. Because if it's not, well, there should be no acceleration. So if the friction force is bigger, well, it's either it's not moving or it should be slowing down. Yeah, it can happen, like in a certain situation that you try to decrease the amount of force that you applied, but the frictional force is bigger. So that means that your acceleration in that particular case would be negative, or it's decreasing in the velocity is decreasing in magnitude, and you have a negative acceleration there. In that particular case, your frictional force must be bigger than the applied force until such time that, yeah, the object will just eventually stop. Okay. So any questions with that example? So again, if you're trying to relate here and apply also the the first and the second Newton's law. So first Newton's law is applicable for objects that are not moving or moving with a constant velocity. Again, acceleration for both cases is zero. And that is the important thing to note about first Newton's law. A is equal to zero. And the second Newton's law, if the net force is not equal to zero, so that means that the object will be accelerating. And the net force, again, the sum of all the forces must be equivalent to the product of the mass times the acceleration of the object. Okay, let's move on to example number 6. A force of 700 newtons. So we have a force of 700 newtons was applied to a 500 kilogram piano, giving it an acceleration of 0.25 meters per second. So this is moving. So you're talking about the kinetic friction. So again, to start, always in this section, this particular unit, you always start with a free body diagram. And make your object again as a dot. And you have, in this case, FG. FG, the magnitude of your FG is just the product of the mass and the acceleration due to gravity. And then you have the normal force. So that is upward. And then there must be an applied force. That is 700 newtons. So you're given that 700 newtons, 0.0. And I'm going to make that one as positive. So to the right is positive. And then this should be accelerating. So the acceleration is to the right also, uh, 0.25 meters per second squared. So there's uh, movement to the right here. So my friction would be to the left. So this is my FF, and I don't know that one. That's a question mark. Okay. And actually, the main question mark is your mu k. So again, looking at the figure itself, I can say that Fn is just equivalent to Fg. So that means that I have an additional information that Fn is just equivalent to my weight. So the magnitude of the normal force and the weight are just equivalent. So that would be, okay. Uh, Maybe perhaps kindly just recheck your example number 5. I think I miscalculated the 70 and 9.8. It should be 686. Yeah, so if you can change that one out, so that should be 886, 886, 686 newtons. So just kind of change that one, 686. It is an example number 6 that this is 500 multiplied by 9.8. That should give you an answer of 4,900 newtons. Okay. So just kind of calculate in example number 5. But anyhow, it should be move forward. So again, mu p is unknown here, but remember, mu p is related to your frictional force. So in my solution, this particular object is accelerating. Okay, so I'm gonna start with my second Newton's law, that the net force acting on the object is equivalent to its mass times its acceleration. So let's see. Again, in our case, the acceleration happens along the x. So just along the horizontal motion of your object. Because the vertical, that's why we can say the normal force is equivalent to Fg. Again, we can say that one because the net force along y is equal to 0. So it must be that the magnitude of your normal force and the weight is just equivalent. So if I can expand my net force is consists of your Fa. So if you can see in the highlighted portion, that is made up of Fa and the negative of Ff. So equivalent to Ma. So you can see here, you can actually solve for the magnitude of Ff here, because Fa is given by 700 minus Ff is equivalent to the mass of the object, which is 500 multiplied by 0.25. So if you gonna evaluate this one out, so the only unknown is your FF, so therefore you can solve for FF in this case. So that would be 125. So This would be your 500 times 0.25 would give you 125. Solving for FF, so FF on one side, that would be 700 minus 125. So just try to follow the algebra. That should give you that value. So FF is for, see, let's see, where did I, so the magnitude of the friction is 575. Right. Okay, 575 newtons. But remember, we're solving for mu k. So what we know that solving for mu k. But we know that mu k is just FF mu k times Fn. So that is just mu k is just equivalent to FF over Fn. So I have the magnitude of the force of friction and then divided by the normal force, which is 4,900 newtons. So if you can see again, I can cancel out my newton. So mu essentially is just a pure number, it's just a number. So it gives you 0.1 here. So 0.12 that should be your kinetic coefficient of kinetic friction. Okay. So any questions so far? Nope. So what I want you to do is I'm gonna group you into 9 or 10, and you answer the last example there. So